Hello there, welcome to my channel on chemistry lessons. Make sure you subscribe and you hit those like buttons to make sure you don't miss out on any future content. Also use the comments and let me know if there's any other videos that you think would be useful. This is an A-level chemistry lesson, and although it does focus on the AQA specification, this is just a concept of KC and is true across all other specifications too. So this is what the specification says then. Now, the big thing here is that we need to come up with an expression for the Kc equilibrium constant, and we start to look at equilibrium constants here. So it's like a quantitative way, there's calculations involved. And we see here up the top, it says equilibrium constant Kc, we'll come to that in a minute, but it says for homogeneous systems. Now, all that means is that all reactants and products are in the same phase. So they're all aqueous or they're all gaseous. So they're on the same phase. So we're going to work our way through the spec then. We're going to look at the expression for Kc. We're going to look at how we calculate Kc and also coming up with the units. And it does add a little bit at the bottom there, which we can link back to Le Chatelier from previous lessons, the qualitative effects of change of temperature. So the little subscript C is telling us it's dealing with concentrations. Further on in second year, you will look at Kp and Ka, so you look at other constants. But this one focuses on Kc, which is equilibrium constants for concentration. Now, concentration is usually a term that we'd use for solutions. However, you can work out the concentration of a gas, so it could be gas or solutions. And just a reminder that we calculate concentration by moles divided by volume, and volume would be in decimeters cubed. When you're given the value for the equilibrium constant Kc, it's usually quoted with a temperature, because the equilibrium constant is a constant. It doesn't change as long as the temperature remains constant. So Kc is specific to a specific temperature. So Kc will change with temperature, but with nothing else. Right, let's have a look at this very, very general equation. So we've got a very general equation. We've got two reactants producing two products. And these lowercase a's and b's, that's the stoichiometry. That's the balancing of the equation. So for example, this could be a 2 or a 1 and a 1 and a 2. So that's your stoichiometry. Now, the equilibrium constant Kc, the expression, is derived directly from a balanced equation. So as you can see, we've got the reactants on the bottom and the products on the top. And this square brackets here, so when you see the square brackets, and I'm going to put square brackets A, that means the concentration of A. That's what it means. Concentration of A in moles per decimeters cubed. So square brackets are important. We must have square brackets. So it's the concentration of the products to the power of their stoich. So this is concentration of C to the power of C multiplied by the concentration of D to the power of D divided by, so it's a ratio, divided by the concentration of A to the power of A and the concentration of B to the power of B. The easiest way to get our head around this is to do a couple of examples. We also need, as you've seen from the spec, that we must be able to come up with the units, because the units will vary. Okay, and this is quite often the most common area that students find difficult. So again, we'll come back to the units. Okay, let's have a look at two examples then. So we'll number them 1 and 2. If you're feeling brave, you can pause the video and have a go at the expressions yourself, and then unpause the video and you can hear me go through them. Alternatively, you could pause after example 1 and have a go at 2 by yourself. Okay, number 1 then. So Kc is going to be the concentration of PCl3 to the power of 1, because there's only one PCl3. Don't need to put that though, we can just leave, because 1 to the power of 1, we don't need to put that. And then it's the concentration of Cl2, again to the power of 1, don't need to write that, all over the concentration of PCl5 to the power of 1. And that's our expression for Kc. How do we work out the units? Well, The clue or the tip is add these stoichs together on the top. So 1 plus 1 is 2. So we end up with moles per decimeters cubed. I'm going to leave that in brackets for now, squared. So we've done 1 plus 1 is 2. And it's divided by moles per decimeters cubed to the power of 1, because there's only 1 on the bottom. Units for concentration is moles per decimeters cubed. So I've got moles per decimeters cubed squared on the top, moles per decimeter squared on the bottom, 2 minus 1. So to remove this from the bottom here, we do 2 minus 1. It's the top take away the bottom. 2 minus 1 is 1. So this is just moles per decimeters cubed to the power of 1, which is just moles per decimeters cubed. So our units are moles per decimeters cubed for the first one there. The units does tend to be what causes some students some issues. The more you practice, the easier it gets. The second one then, number 2, the expression for Kc this time is the concentration of SO3 to the power of 1 divided by the concentration of SO2 to the power of 1 multiplied by the concentration of O2. This time it's to the power of a half. I'm just literally using the stoichiometry in the equation. So that's my expression for Kc. How do we do the units? Well, the sum of the top is 1. The sum of the bottom is 1.5. So it's moles per decimeter cubed to the power of 1 minus 1.5. 1 minus 1.5 is a half. So, sorry, it's minus a half. 1 minus 1.5 is minus a half. And now we need to simplify this somewhat. So moles, it's moles to the 1, dm to the minus 3. So there's kind of an invisible 1 there. And when we multiply out the brackets, we are going to multiply through the indices. So 1 times minus a half is minus a half. So it becomes mol minus a half. And then minus 3 times minus a half is plus 1.5. So it's dm 3 over 2, which is 1.5. So the units are awkward, and to be fair, that one there that we've just done, number 2, is as hard as anything you'd be expected to do or come across. So practice makes perfect here. Let's move on to looking at an example then. So we have to do a calculation here. So again, we'll stick with a general equation. So it's 2a plus b, equilibrium 3c plus d. So if we were asked for an equilibrium expression, we would come up with Kc is equal to the concentration of C to the power of 3 multiplied by the concentration of D to the power of 1 divided by the ratio as concentration of A squared multiplied by the concentration of B. And in terms of units, it's going to be moles per decimeters cubed to the power of 4 divided by moles per decimeters cubed to the power of 3. 4 minus 3 is 1. So our units here will be moles per decimeter cubed. But that's not what this question is asking us to do. Here we've been given the initial moles of A, so we've been told that the mixture contained, or initially the mixture was prepared using 2 moles of A. So I'm going to say there are 2 moles of A at the beginning, and there's 1.5 moles of B. That's what's been added together. And then they've allowed this mixture to reach equilibrium. We know the equation, we can see there, and we are told that the equilibrium moles of B is 0.74. And now we're asked to calculate the amount of A, C and D at equilibrium. So let's think logically about this then. What's happened? So using the information we've been given, we can see that the moles of B have gone down by 0.76. That's what's happened. It's gone from 1.5 to 0.74. And now what we do is we'll use the stoichiometry, and that means that D will increase by the same amount as B because it's a 1-to-1 ratio. If the reactant is going down, the products are going up. That means that D will increase by 0.76, C will increase by 3 times 0.76. Stoichiometry is 3 to 1. And A will decrease by 2 times 0.76. And then we can easily simply derive the final number of moles. So this will just be 0.76. This will be 3 times 0.76. And this one here will be 2 minus 2 times 0.76. And that's our equilibrium moles. And if we had the volume, which we don't here, if we had the volume, we could then turn into equilibrium concentrations, and we could actually calculate the value for Kc, because we would know to the concentration of C to the power of 3 multiplied by the concentration of D divided by concentration of A squared multiplied by concentration of B. So you can see how once we can do this table, we can take it a step further and can actually calculate values for Kc. So I recommend that you do work under a balanced equation and almost visualize a table as we've done here. So initial moles, the reacting moles, and then any equilibrium moles. So this time you may wish to pause the video and have a read and a go at this one yourself, and then when you're ready, unpause and have a look. Okay, so the starting point for what I suggest you do is have a balanced equation, and then we visualize that table underneath the equation. So we have a start, we'll have some sort of change, and then we'll have equilibrium at the end. So here we have a mixture of 10 moles of nitrogen. So at the start we have 10 moles of nitrogen and 25 moles of hydrogen. We don't have any ammonia at the start. They were allowed to reach equilibrium, and at equilibrium we are told that we have 2.8, wrong place. So we have 2.8 moles at equilibrium of nitrogen. So what's happened? Well, the nitrogen has gone down. We can see that. How much has it gone down by? It's gone down by 7.2. So what will happen is this will go down by 7.2 times by 3, and this will go up by 7.2 times by 2. So we have 14.4 here, and if we do 25, take away 7.2 times by 3, we'll have 3.4 here. And is that all I'm asked to do? That is all I'm asked to do. Okay, I could have been, now if this was an exam, I could have been asked for an expression for Kc, I could have been asked to calculate a value for Kc, I could have been asked for units of Kc. But let's move on to a real exam question then. So this is a very typical, and I suppose, dare I say, straightforward style exam question on Kc. So here, 7 marks, allow yourself around about 7 to 10 minutes. So pause the video and have a good go at it, and when you're ready, unpause and we'll go over it. Okay, so advice for question 1 when we're asked about the amount in moles. Have a balanced equation that we're going to work from and work as if it's a table underneath. So here we go. We've got start, and then we've got change, and then we've got equilibrium. And what are we told? We are told that we have 1.50 moles of NO, and they're mixed with 1 mole of Cl2. Don't always assume there's no product at the start, because sometimes they'll be a bit sneaky and they'll throw some in, but again, there isn't in this case. And we are told that equilibrium contains 0.350 moles of NaCl. So what we can see is that the NaCl has gone up by 0.350. That means that the NO will have gone down by 0.350 because it's a 2 to 2 ratio, and in fact the chlorine will have gone down by half this amount. So what I'll do is I'll do 0.35 divided by 2. So this will have gone down by 0.175. Okay, so now what I'll do is find my moles of chlorine, which is 1 minus 0.175. So my moles of chlorine at equilibrium is 0.825. My moles of NO will be 1.5 minus 0.35, which is 1 0.15. And that's the correct answers for those two. For B, give an expression for the equilibrium constant for that equilibrium. So Kc is equal to the concentration of NaCl, square brackets is essential, to the power of 2, all over square brackets NO squared multiplied by the concentration of Cl2. There we go. Okay, moving on to part C. A different equilibrium is prepared in a flask of volume 800 centimeters cubed at a different temperature. Equilibrium mixture contains, so they're telling me the number of moles it contains, and for this we're given Kc, and they want us to determine the amount of moles of NaCl. So we're using the same equilibrium Kc expression, but I'm going to rearrange it a bit because I'm trying to calculate the moles of NaCl. So I'm going to rearrange it to get NaCl concentration. So what I'm going to do is, if I have Kc multiplied by the concentration of NO squared multiplied by the concentration of Cl2, that's going to be equal to my concentration of NaCl squared. So what I'm going to do is I need to convert these moles into concentrations because the equilibrium expression works in concentrations. That's what these square brackets means, and the question has given me moles. So I'm going to have to work out the concentration. So I'll do that up here. Concentration of NO is going to be the moles over volume. That's what concentration is. Concentration is moles over volume. The volume is 800 centimeters cubed, but I must work in decimeters. So that's 0.8. So I'm going to go 0.85, get my calculator, 0.85 divided by 0.8, that is equal to 1.0625. And now I need my concentration of Cl2. I'll do that here. Concentration of Cl2 is moles over volume, which in this case is 0.458 divided by 0.8. Work that out. 0.458 divided by 0.45. Can't use my calculator. 0.458 divided by 0.8 is 0.5725. So now what I'm going to do is I'm going to work out this value here. So it's going to be Kc, which is 1.32 times 10 to the minus 2. I'm given that in the question, look. I'm going to times that by my concentration of NO, 1.0625, but that must be squared. And I'm going to times it by the concentration of Cl2, but doesn't need to be squared. It's just 0.5725. So put that into my calculator. Times by 1.0625 squared times by 0.5725, and I have a value here at 0.008531, and that is equal to NaCl squared. So I'm going to take the square root of that. So the square root of 0.008531, that's going to be equal to my concentration of NaCl. So I'll just do that on my calculator. .008531 square root is equal to 0.092364. Now that's my concentration of NaCl. I've been asked for the amount of moles, and using our expression, concentration is moles over volume. So moles is concentration times volume. So I'm going to times this concentration by the volume, which is 0.8. So times my answer there by 0.8. And I end up with a value here of 0.0739. There's an awful lot of working out to get to that value there. I've used 3 significant figures because that's the minimum amount in the question. Kc is 3 significant. The moles of those two are 3 significant. So there's an awful lot of working out for those 4 marks. Well done if you got that right. And unfortunately, as sad as it is, that brings this lesson to an end. Remember to like the video, subscribe, comment for any other videos that you think are missing. I'm trying to fill in as many blanks as I can, so I will work on those videos that people ask for first. And good luck in any exams that you've got. Goodbye.